A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
My Weird Prompts is a community-driven initiative exploring how AI can fuel curiosity and uncover the fascinating ways our world works. GPU compute for this podcast is generously provided by Modal. Learn more at modal.com.
I was looking at some satellite imagery of the Pacific Spaceport Complex on Kodiak Island, Alaska the other day, and it is just such a stark, isolated place. It makes you realize the sheer logistical absurdity of what we are talking about today. We are looking at the process of moving an entire ecosystem of Israeli-developed defense technology, radars, launch canisters, and command centers, thousands of miles across the globe to the middle of the North Pacific, just to see if it works. Today's prompt from Daniel is about the methodology and challenges of testing high-stakes missile defense systems like the Arrow, specifically focusing on those intensive, high-latitude tests conducted in Alaska.
It is a massive undertaking, Korn. Herman Poppleberry here, and I have been diving into the technical reports from these test campaigns, including the most recent data coming out of the early 2026 evaluation cycle. People often think of a missile test as just pushing a button and watching a rocket go up, but when you are dealing with the Arrow 3 or the upcoming Arrow 4, you are testing a system of systems. You are moving hundreds of personnel and tons of sensitive hardware into an environment that is the polar opposite of the Negev desert where these systems were born. We are talking about a transition from arid, sandy heat to sub-zero, salt-sprayed maritime conditions.
Which raises the obvious question of why. If you have the Mediterranean right there, and you have established desert testing ranges in Israel like the Palmachim Air Base, why go through the nightmare of shipping everything to a remote island in Alaska? Is it just about having more room to breathe, or is there something specific about the geography that you simply cannot replicate at home?
It is primarily about the geometry of the engagement and the safety of the flight corridor. In the Mediterranean, you are very constrained. You have some of the busiest commercial flight paths in the world, dense shipping lanes, and the proximity of neighboring countries that might not appreciate a kinetic kill vehicle falling into their territorial waters. To test a high-altitude, exoatmospheric interceptor like Arrow 3, you need a massive amount of cleared space. You need to be able to launch a target missile that mimics a long-range ballistic threat, something that climbs high into the atmosphere and then comes screaming back down at hypersonic speeds. You need the interceptor to have the room to perform its maneuvers in space without any risk of debris falling on a populated area. Alaska provides that long-range flight corridor over the open Pacific that simply does not exist in the crowded airspace of the Middle East.
Right, and I imagine the safety margins for something like a kinetic kill vehicle are pretty intense. If you miss, or even if you hit, you have a lot of high-velocity scrap metal coming back down. But beyond the space, I want to talk about the environmental shock. We're talking about hardware designed for the heat of the Middle East being dropped into sub-zero Alaskan temperatures. Does that actually change the physics of the interceptor?
It changes almost everything about the pre-launch phase and the structural integrity of the vehicle. One of the biggest technical hurdles is what engineers call cold soaking. When that Arrow 3 interceptor sits on a launch pad in Kodiak, the extreme cold affects the viscosity of the lubricants in the gimbal systems and, more importantly, the physical properties of the solid propellant. Arrow 3 uses a two-stage solid propellant motor. At very low temperatures, the solid fuel, often a composite like hydroxyl-terminated polybutadiene, can reach its glass transition temperature. This makes the propellant grain brittle. If you have a micro crack in your propellant grain because of the cold, the surface area for combustion increases instantly when you ignite it. That leads to a catastrophic overpressurization of the motor casing.
So you are basically turning the missile into a pipe bomb if the temperature management fails. That sounds like a high-stakes engineering problem before you even get to the guidance systems. Do they have to heat the canisters, or is the goal of the Alaska test specifically to see if the missile can handle that thermal stress without help?
It is a bit of both. They use environmental control systems within the canisters to keep the hardware within a specific operating band, but the Alaska tests are designed to push those limits. You want to validate that your thermal protection systems work, but you also want to see how the sensors behave. Think about the seeker head on the interceptor. It is an electro-optical sensor designed to pick out a tiny, cold target against the blackness of space. In Alaska, you have different atmospheric conditions, different moisture levels in the lower atmosphere, and a different infrared background compared to the desert. If your sensor calibration is off by even a fraction because of the ambient temperature of the hardware, you might lose the target during that final, critical, high-velocity closing phase.
That closing phase is where the real magic happens, or the real failure. We're talking about two objects hitting each other at combined speeds that are just difficult to wrap your head around. I think we mentioned this in a previous discussion, but the Arrow 3 does not use an explosive warhead, right? It is purely hit to kill.
That is correct. It is often described as hitting a bullet with another bullet, but it is more like hitting a fast-moving needle with another needle while both are traveling at several kilometers per second. Because it is a kinetic interceptor, you do not have a blast radius to compensate for a near miss. You have to be perfect. The Alaska tests allow them to push the envelope on that precision. They can launch the target missile from a high-altitude carrier aircraft, like a modified C-17, or from another site like the Pacific Missile Range Facility, creating a much more realistic, high-velocity terminal phase than they could safely do in a smaller range.
And that brings us to the sensors on the ground. You cannot have a successful intercept without the brain of the operation, which is the radar. We did a deep dive on the Green Pine radar back in episode 1000, and I remember us talking about its massive power output and its ability to track targets at incredible ranges. When they move a Green Pine unit to Alaska, how does it integrate with the existing American infrastructure? Is it just a standalone test, or are they plugging the Israeli radar into the United States Missile Defense Network?
The integration is actually one of the most critical parts of the methodology. During the Alaska campaigns, the Green Pine radar has to talk to the United States Satellite Early Warning Systems and the ANTPY-2 radars. This is where the data link latency problem comes in. If you are tracking a ballistic missile that is traveling at Mach 10, every millisecond of delay in your communication loop translates into a massive error in your projected intercept point. Testing in Alaska proves that the Israeli fire control software can ingest data from American sensors via Link 16 or other advanced data architectures and output a firing solution in real time, despite the geographical distances.
I find the latency issue fascinating because we are talking about the speed of light for the data, but the processing time is where the bottleneck happens. If the Green Pine is seeing the target, but the Fire Control Center is waiting for a confirmation from a satellite over the Pacific, you are losing precious seconds. Did they find that the Arctic atmosphere messed with the radar signal at all? I know the ionosphere can be a bit more active up there with the auroras and all that.
The signal-to-noise ratio is definitely different. You have high-latitude atmospheric interference and ionospheric scintillation that you just do not see at the equator or in the Middle East. The Green Pine has to be able to filter out that atmospheric noise to maintain a solid track on the target. What is really impressive is how they use these tests to refine the autonomous engagement algorithms. Because the Alaskan range is so empty, they can let the system run with a much higher degree of autonomy than they would elsewhere. They want to see if the AI-driven fire control can make the right decision without a human, in the loop, having to verify every single step of the process.
That sounds a bit nerve-wracking, letting a high-altitude interceptor make its own calls in a live-fire test. But I guess that is the point of high-stakes testing. You want to find the failure points where no one gets hurt. You mentioned the Arrow 4 earlier. Is the work they did in Alaska with Arrow 3 directly feeding into the development of the next generation?
We are currently seeing the fruits of that labor as Arrow 4 enters its advanced testing phase in early 2026. One of the big goals for this next phase is dealing with maneuverable reentry vehicles, or MARVs. We talked about these in episode 1398. These are targets that do not just follow a predictable ballistic arc, they can shift their trajectory as they re-enter the atmosphere to dodge interceptors. To test against a MARV, you need a massive amount of downrange space because the interceptor has to be able to react to those unpredictable movements over hundreds of miles. Alaska is essentially the only place where the United States and Israel can safely simulate a high-speed chase in the upper atmosphere.
It really highlights the shift in the threat model. It is no longer just about stopping a Scud missile that flies like a tossed rock. It is about stopping something that is actively trying to dodge you. When you look at the telemetry data coming out of these tests, what are the engineers actually looking for? Is it just a hit or miss, or is there a more nuanced metric of success?
The hit is the ultimate validation, but the telemetry tells the real story. They're looking at the Divert and Attitude Control System, or DACS, on the kill vehicle. This is the set of small thrusters that steer the interceptor in the final seconds. In the vacuum of space, you do not have fins to steer with, you have to use these tiny rocket bursts. They want to see how much fuel was used, how quickly the thrusters responded to the sensor data, and whether the structural integrity of the kill vehicle held up under the extreme g-forces of those final maneuvers. Sometimes the test is considered a massive success, even if there is not a physical collision, as long as the interceptor passed within the lethal distance and all the subsystems performed as expected.
I think people underestimate how much of this is a software game. The hardware is incredible, obviously, but the ability to calculate a closing solution at those speeds is a monumental feat of coding. It makes me think about the distributed architecture we discussed in episode 997. If you have sensors in Alaska, satellites in orbit, and a fire control center potentially being monitored halfway around the world, the coordination is just staggering.
It is the ultimate system of systems, and that is why the Alaska tests are so important for the strategic partnership between the United States and Israel. It proves that these two nations can combine their most sensitive technologies into a single, cohesive shield. It is not just about the Arrow missile itself, it is about the entire infrastructure of global missile defense. When the Arrow 3 successfully intercepted a target over the Pacific, it was a signal to the rest of the world that the technology had matured beyond the regional level. It is now a global class system. This has become even more relevant with the recent deployment of Arrow 3 systems to Germany as part of the European Sky Shield initiative. The Alaska data proved the system could handle the cold European winters.
There is also a political and strategic depth to this. By testing in the United States, Israel is essentially validating its technology against the highest American standards. It is a massive vote of confidence from the Pentagon to allow these tests to happen on American soil, using American target missiles. It cements that alliance in a way that 100 diplomatic meetings never could.
You are spot on. And from a technical perspective, it allows for a level of stress testing that you just cannot get in a lab. You can run 10,000 simulations, but a simulation will never capture the exact way the wind shear at 40,000 feet affects the initial boost phase, or how the specific electromagnetic environment of the Arctic affects a radio frequency seeker. You need the physical reality of the flight test to find the bugs that the simulations missed. For instance, the way the salt air in Kodiak might affect the electrical connectors on the launch pad, that is something you only learn by being there.
So, for the listeners who are interested in the practical side of this, how does one even keep track of when these things are happening? I know they do not exactly put out a press release a month in advance saying, "Hey, we are launching a missile on Tuesday," but there are ways to see the footprints of these tests, right?
There are. If you know where to look, you can follow the public notices to air missions, or NOTAMS, and the notices to mariners. When a test is scheduled at Kodiak, the Federal Aviation Administration and the Coast Guard have to issue alerts to clear the airspace and the shipping lanes. You will see these massive, strangely shaped exclusion zones appear on the charts. For the aviation nerds and the defense observers, those NOTAMS are the first clue that something big is about to go up. It is a great way to see the real-world footprint of these systems. You can literally see the flight path mapped out in the restricted zones.
I love that. It turns the whole thing into a bit of a detective game. You see a giant rectangle of closed airspace over the North Pacific, and you know the engineers in the bunkers are sweating over their consoles. What do you think the biggest takeaway is for the average person who follows this? Is it that we are safer, or that the technology is just getting more terrifyingly complex?
I think it is the realization that defense is much harder than offense. To launch a ballistic missile, you just need to get the physics of the arc right. To stop it, you need a global network of sensors, sub-millisecond communication, and a kinetic interceptor that can survive the transition from a desert climate to the Arctic and then into the vacuum of space. The Alaska tests prove that we are actually winning that race, but it requires a level of international cooperation and engineering discipline that is almost unparalleled in any other field.
It is a testament to what happens when you have a clear goal and the best minds in the world working on it. And frankly, seeing the Arrow 3 perform in those conditions makes you feel a lot better about the strategic stability of the world. It is a shield that actually works, not just on paper, but in the most hostile environments on Earth.
It really is. And as we look toward Arrow 4 and the integration of even more advanced sensors, that testing methodology is only going to get more rigorous. We are moving toward a world where the defense architecture is essentially plug and play across different continents. If you can make it work in Alaska with Israeli hardware and American satellites, you can make it work anywhere. We are seeing this interoperability become the standard for the next decade of defense planning.
That is a powerful thought to leave people with. The idea of a global, interoperable shield that can be deployed wherever the threat emerges. It takes the concept of strategic depth to a whole new level.
It also changes the calculus for any adversary. If they know that their most advanced maneuverable warheads are being tracked and intercepted in live-fire tests in the most difficult conditions imaginable, the deterrent value of those weapons drops significantly. Testing is as much a part of the deterrent as the deployment itself. It shows the world that the shield is not just a theory, it is a proven reality.
Well, I think we have thoroughly covered the frozen frontiers of missile defense today. It is a fascinating blend of high-level physics, logistical nightmares, and global politics.
It definitely kept me busy this week. There is always more to find when you start digging into the test reports and the telemetry analysis.
Before we wrap up, I want to give a huge thanks to our producer, Hilbert Flumingtop, for keeping the gears turning behind the scenes, and a big thank you to Modal for providing the GPU credits that power the research and generation of this show. We literally could not do this without that compute power.
This has been My Weird Prompts. If you want to dive deeper into the archives, check out our website at myweirdprompts.com. You can find all the episodes we mentioned today, including the deep dives on the Green Pine radar and the Arrow system architecture.
And if you are enjoying the show, do us a favor and leave a review on your favorite podcast app. It really does help other people find these deep dives and helps us grow the community. We will be back next time with another prompt from Daniel.
See you then.
Goodbye.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from slow takes to facts on cue. We change and follow through. My Weird Prompts, that's the close from sloth, from man, from long-eared host. My Weird Prompts, until next time, stay curious, keep weird.